Welcome to the second video in our series on linear programming. This video will take us through the graphical method. Let us consider our learning objectives for this video. First, we need to learn how to formulate the problem algebraically. This can be done by first identifying and developing the input constraints. Once this is done, we will develop the objective function. Remember, we are trying to either maximize or minimize the objective function depending on our goals. Once we have plotted the input constraints and the objective function on a graph, we will solve the problem by either reading the answer off the graph or through simultaneous equations. Now remember here that the graphical method can only be used if we have two products. Any more than two products, and we need to use the simplex method, which we will look at in our next video. In order to achieve our learning objectives, we are going to work through the example on screen. The objective in this example is to maximize our contribution. Before we begin, let us break the graphical approach into some understandable steps. The first thing we want to do is to identify the constraints and plot these constraints on a graph. Once we have plotted these constraints, we will be able to identify the feasible production area. We then determine the objective function and can plot this on the graph. As we are trying to maximize our contribution, we want to find the furthest point from the origin where our objective function touches the feasible production area. So let us look at the information again and develop our constraints. First, we see that our materials are limited to 3,440 units. We see that product A uses 8 units of materials, while product B uses 4 units. We can therefore develop our constraint equation for materials as 8 multiplied by the production of A plus 4 multiplied by the production of B must be less than or equal to 3,440 units. We can write this constraint mathematically as shown on screen. We can then plot this constraint on our graph. How do we do this? To plot any line, we need 2 points. To get our first point, we assume that we produce 0 units of B. Now all 3,440 material units are committed to product A. So how many units of A can I make? And we see that I can make 430 units of A, being the 3,440 divided by 8. Next, we assume that we produce 0 units of A and ask how many units of B can I produce. Following the same logic, we find that we can produce 860 units of B, being the 3,440 units of materials divided by 4 units of material per unit of B. Now we have 2 points in our graph and we can plot this on our set of axes. When we produce 430 units of A, we produce 0 units of B. When we have 0 units of A, we have 860 units of B. The feasible production area is then anywhere under the curve, which is now highlighted in blue. We then move on to our next constraint, where we see that labor is limited to 5,760 hours. We also see that product A uses 12 labor hours, while product B uses 16 labor hours. Thus, whatever combination of A and B we produce, we must use 5,760 labor hours or less. We can express this constraint mathematically as 12 multiplied by product A plus 16 multiplied by product B must be less than or equal to 5,760 labor hours. We can now add the labor constraint to our materials constraint. We write this constraint mathematically as shown on screen. We follow the same process to plot the labor constraint. To get our first point, we assume that we produce 0 units of B. Now all 5,760 labor hours are committed to A. How many units of A can I make? And again, I can make 480 units of A, being the 5,760 labor hours divided by 12. Next, we assume that we produce 0 units of A and ask how many units of B can I produce. Following the same logic, we can produce 360 units of B, being the 5,760 labor hours divided by 16. Now we have 2 points in our graph and we can plot this on a set of axes. When we produce 480 units of A, we have 0 units of B. When we have 0 units of A, we have 360 units of B. What you will now notice is that our feasible production area has shrunk. It is no longer constrained by just the blue materials line, but also by the orange labor hours line. The area highlighted in orange represents our new feasible production area. Our third constraint is machine capacity of 5,520 machine hours. We also see that product A uses 8 machine hours, while product B uses 10 machine hours. Whatever combination of A and B we produce, we must use 5,520 machine hours or less. Pause this video and see if you can develop this constraint and plot it on the graph on your own. Good job! We now have the machine constraint on screen. We follow the same process as materials and labor to plot the constraint. To get our first point, we assume that we produce 0 units of B. Now all 5,520 machine hours are used for A. How many units of A can I make? And we find that we can make 690 units of A, being the 5,520 machine hours divided by 8. Next, we assume that we produce 0 units of A and ask how many units of B can I produce? Following the same logic, we can produce 552 units of B, being 5,520 divided by 10. Now we have 2 points in our graph and we can plot this on our set of axes. When we produce 690 units of A, we have 0 units of B. When we have 0 units of A, we have 552 units of B. Now this constraint falls outside our feasible production area. This means that when considering our labor and materials constraints, machine hours does not actually constrain us any further. Therefore, our feasible production area remains unchanged. Our final constraint is the maximum market demand. We see that product A is limited to 450 units, while B has no maximum. This is a constraint because if we produce more of product A than the market is demanding, we won't be able to sell those units and we will be wasting resources. Also, 2 further constraints are that sales for both products A and B must be greater than or equal to 0. We cannot have negative production for our products. So we can add these last constraints as shown on screen. The yellow line now represents the maximum sales for product A. The X and Y axes represent the minimum sales for products A and B. Based on all these constraints, we can identify our feasible production area, and we can see that it is mainly influenced by the materials and labor constraints. Once we have identified the production constraints and found our feasible production area, our third step is to determine the objective function. For this scenario, our goal is to maximize the contribution from products A and B. How would we calculate our combined contribution for products A and B? We know that the contribution per unit of A is 20 Rand, while the contribution per unit of B is 24 Rand. Therefore, our contribution would be calculated. Therefore, our total contribution would be calculated as 20 Rand multiplied by A plus 24 Rand multiplied by B. We can write our objective function out as maximize C equals 20A plus 24B. To plot this objective function on the graph, we assume a random contribution number. Let us assume 6,000 Rand. We then ask ourselves, how much of A must I produce to make 6,000 Rand if I don't produce any of B? And we see here that we get 300 units, being the 6,000 Rand divided by the 20 Rand contribution from product A. Likewise, we do the same for B, and here we arrive at 250 units, being the 6,000 Rand total contribution divided by the 24 Rand contribution from product B. We can now plot our objective function on the graph. Now we slide this line using a technique such as the sliding set square until it reaches the furthest point possible from the origin. Here we see that the last point where our objective function touches our feasible production area is at the intersection of the material and labor constraint, which I have highlighted as point X. We can now read the point off the graph to get our optimal production of products A and B. However, reading off a graph can be problematic, as the optimal solution can be difficult to see. To address this issue, we can use simultaneous equations to solve. So we know that point X is our optimal solution. Point X is the point where the blue material constraint and the orange labor constraint intersect. Thus, we need to solve these constraints simultaneously. To do this, we first change the less than or equal to sign to an equal sign. Now, there are various ways to solve simultaneous equations. You need to use a method that you are comfortable with. For this example, I am going to use the technique of making the B's equal. To achieve this, I can either multiply the materials constraint by 4 to arrive at 16B, or divide the labor constraint by 4 to arrive at 4B. Let us divide the labor constraint by 4, and we end up with 3A plus 4B is equal to 1,440. Now that the B's are the same in both constraints, I will subtract the labor constraint from the materials constraint. Notice how I have changed the signs to negatives in the labor constraint. I then end up with 5A is equal to 2,000, and I can solve for A as 2,000 divided by 5 is equal to 400. I can now substitute this value of 400A into either the materials or labor constraint. For this video, I will use the materials constraint. So I end up with 8 multiplied by 400 plus 4B is equal to 3,440. I can now solve for B to arrive at 60 units. Therefore, my optimal production mix is 400 units of A and 60 units of B. How would we now calculate the shadow price of a resource? Remember, the shadow price is the opportunity cost. It represents the loss or gain in contribution from a 1 unit decrease or increase in the scarce resource. So, from our example, we know that the relevant constraints are materials and labor. We can calculate the shadow price of materials by increasing our available materials by 1 unit. So instead of having 3,440 units of materials, we now have 3,441 units. Once again, we need to solve the equation simultaneously to find our new optimal production mix. Pause this video and give it a try to see what you come up with. Okay, so following the same process we used to solve our previous equation, we arrive at an optimal solution of 400.2 units of product A and 59.85 units of product B. Now that we have the revised units, we can calculate the change from our original production of 400A and 60B. We see that product A has increased by 0.2 units, while product B has decreased by 0.15 units. We now multiply this change by the contribution for each product. Remember, product A had a contribution of 20 Rand, while product B had a contribution of 24 Rand. We can then multiply this out and sum the changes in contribution to arrive at the shadow price of 40 cents. Therefore, the company will be willing to pay up to 40 cents more than the current purchase price per additional unit of materials. We can apply the same logic to calculate the shadow price of labor. This brings us to the end of the graphical approach to linear programming. In our next video, we will look at the simplex method of linear programming. Thank you.